So we just talked about prime numbers, and now we're going to do something with them called prime factorizations. And we are going to use these regularly. They're really helpful for things like reducing fractions. They're really helpful for what we're going to do next, which is calculating least common multiples of numbers and expressions, or greatest common factors. So they're going to come into play a lot, and they're also going to help us see how numbers can be used flexibly. That's a big goal of mine, is to teach you how numbers can be used flexibly. So you might have seen these before. I'm going to start with the number 25. And what we're going to do is we're going to write the prime factorization for the number 25. And we're going to use something called a factor tree. It's just a little tool. It's a visual. And what you do is you ask yourself what times what equals 25. And hopefully you come up with 5 times 5. So we're going to make 2 branches that come off 25. Now, I don't know why they call it a factor tree if it's going down and not up, but whatever. So each factor goes at the bottom. 5 times 5. These numbers should multiply to be the number above it. Well, they're called prime because what we want are prime numbers at the bottom. And if you recall from our previous conversation, 5 and 5 are both prime. So I always like to circle them once we get done. So 5 and 5 are both prime. So this factor tree is done, but it's not the prime factorization. The prime factorization is stating the numbers that are all multiplied together like as a multiplication statement. So 25 is equal to 5 times 5. This is the prime factorization, that thing that you see right there. It's the product written out. Or you can also do prime factorizations using exponents. In this case, it would be 5 to the second power. Okay, so what we're doing is we're breaking the number apart. Prime numbers are like the DNA of the number, right? 25 is built using 5 and 5. That's why we call it a composite number. It's composed of 5 and 5. Let's do another one. I like this one because I'm gonna show you how numbers can be used a little flexibly. 36. So pause the video and try to do it. I'm gonna keep going. 36 can be done a number of different ways, and I'm gonna do it every possible way. 36 could be, I'm guessing many of you might have done 6 times 6. And 6 is not prime, is it? So both of these, we have to continue the branches. 6 is 2 and 3. 2 times 3, right? We're multiplying. Both of those numbers are prime. This 6 is also 2 times 3. And both of those numbers are prime. So notice we have 4 different numbers. 2, 3, 2, and 3. The way we tend to do it is we write them out from smallest to greatest. That's just a convention. So we're going to do that. 2 times 2 times 3 times 3. We can rearrange this because of which property? The commutative property. Or we can also write it using exponents. 2 to the second, because there were 2 of them, times 3 to the second, because there were 2 of them. Now, not all of you might have done it like that. Some of you might have done it like this. You might have said 36 is 4 times 9. Maybe that's the thing that came to your mind. 4 is 2 times 2, which are both prime. 9 is 3 times 3, which are both prime, right? But look, it's the same numbers, 2, 2, 3, and 3. Some of you might have even done it like this. 36 is 2 times 18. 2 is prime, but 18 is not. So this is where one branch gets longer than another branch, because we have to keep going with the 18. 18 is, well, here you could do it 3 times 6, or maybe you just kept dividing by 2 and said 2 times 9. You get 2. 9 is then 3 times 3. Keep going until you get prime numbers. But look, it's the same numbers every time. 2, 2, 3, and 3. And then I'll do it the last way. And it's also starting out 2 and 18, But then instead of 2 and 9, you could do 3 and 6. 3 is prime, 6 is not. Keep going with the 6. 2 and 3. So what you're going to find here is that the number 36, no matter which way you slice it up, it's going to be composed of these 4 prime numbers. But in any order, if we start putting them back together, we could end up with 4 times 9, 2 times 18, 6 times 6. But they're all going to take us back to the number we started with, right? 36 has this unique blueprint of these 4 prime numbers that compose it, that make it up, okay? Every composite number is like that. It's got its own unique combination of prime factors, because this is prime factorization. Let's try another one. 44. Every single one of these, I want you to pause it, try it, do it. I'm going to keep going. 44, well, you have options. I'm going to pick what probably is the obvious one. Might not be, or I'm just guessing the one I thought was done the most, 4 times 11. Are either of these prime? Yes, 11 is prime, but 4 is not, so we keep going. 2 and 2. 2 is prime, 2 is prime. We're done. No, we're not. We have to write it out. This is not a prime factorization. This is a factor tree. This is a prime factorization, or 2 squared times 11. Either one of these are fine, right? In fact, they're both useful because both of those formats will be useful for doing different things with our prime factorizations. I'm going to put 2 numbers up at once. These will be our last 2 that we do. Try 70 and try 600. Pause the video and then come back. 70, I would approach it. The thing that jumps out to me would be 7 times 10. But you could do 2 times 35. That would also work. 7 is prime. 10 is not. 10 is composite. So we could do 2 times 5. Both of which are prime. So no matter which way you go, 70 ends up with these 3 prime numbers. I like to put them in order from least to greatest. 2 times 5 times 7. This is our prime factorization. This is not. This is. Then the last one, 600. You're like, what? That's a huge number. But when you start dividing it, when you start factoring it, it breaks apart pretty quickly. So the thing that jumps out to me would probably be 6 times 100. That's the thing that jumps out to me. Neither of those numbers are prime, but 6 can be broken into 2 and 3. I don't like the word broken. I should have said factored. Factored into 2 and 3. 100, not prime. You could do 2 times 50, 4 times 25. I'm going to choose 10 times 10. Watch out on these for accidentally thinking addition. That's one of the biggest mistakes I see is you might be checking your work. Why did I get the wrong answer? Sometimes I'll see like 50 and 50 there. So watch out. It's always multiplication. 10 can be factored, divided into 2 times 5. And then this one also is 2 times 5. So our prime factorization is, I'm going to run out of room here. I'm just going to bring it down here. 600 is equal to, I've got 3 2s. So 2 times 2 times 2 times a 3 times 2 5s. That's 5 times 5. If we condense it into exponential notation, 2 to the third times 3 times 5 to the second. Either of these will work for your prime factorization of 600.